Hello everybody, Mark Reef here. This video is intended for AP Physics C teachers who are perhaps new to AP Physics C or even new to calculus or just really rusty on their calculus. This video is about U-substitution, and it's a quick introduction to the topic of U-substitution with a couple of examples. So here's a funny cartoon from XKCD. It's really not going to be this bad, but notice differentiation is presented as a pretty simple flowchart. Integration is a really complicated one. It's often said that differentiation is mechanics and integration is an art, but really it won't be that bad in AP Physics C, I promise you. So I'm going to show you some examples with indefinite integrals. Enough to get you pretty far if you understand them and can apply them. I'll show you where to get some practice as well. So U-substitution is often called the reverse chain rule. It's sort of like undoing the chain rule in a sense. We use it when the integrand is complicated, complex, and we can't see immediately how to integrate. So the technique is just to find a known integral by simplifying what we have and changing our variable to u and looking at it with respect to du. If you don't know what that means, by the way, I'll show you in a moment. This is Unit 6 in AP Calculus, so it is taught in Calculus AB. There are, I believe, 10 units in AP Calculus, and the last two units, 9 and 10, I think, are solely in Calculus BC. So this is about the middle of the curriculum, but it would be in Calculus AB if it's taught as a year, which it usually is, be later on in the course, probably second semester. My students who are Calculus AB students are a little bit tentative with U-substitution. It's not very natural to them until possibly later in the year. There are a specific class of problems where we see this a lot in Physics C mechanics of velocity-dependent drag force problems. I'll show you an example of a recent one in just a moment. And in Physics C electricity and magnetism, you might use it when you derive an equation for RC circuits. There are other places probably as well that I'm not thinking of right now. So here's an example of a simple integrand. If we look at this, we can see that if we integrate that, we're going to get negative 1/2 1 over t squared. We can just do that in my head because it's a very common integral with a simple form. Here's a more complicated integral. It's not really that bad, but it does look a little bit forbidding, and if you're new to calculus, you'll be going, what the heck would I do with that? Because this stuff inside has got these t's in it. It's not as simple as the simple integrand. Well, let's look at what you can do with that. So here's our complicated integrand from before. If we take u to be something inside here and then calculate a du, we're going to rewrite this in terms of u and du. So the natural thing to do is to look inside this parentheses. May not be natural to you, but it will be eventually, and say, okay, well, we can take u to be t to the fourth plus 2t. And then du is 4t cubed plus 2. If we look back at our integral, then we see, okay, this numerator is du over t2 because 4t cubed over plus 2 is twice 2t cubed plus 1. So then this would be du over 2 on the top, and on the bottom we would have u cubed. So that's something that we can deal with. That's relatively easy to do. So we can change our variables and rewrite it in terms of du and u, and it becomes 1/2 integral of du over u cubed. Now we can just calculate an answer. And it's a little more complicated than the previous example, but not terrible. So 1/2 integral of du over u cubed is 1/2 times 1 over negative 2 times 1 over u squared. It's just using the antiderivative. And then we put in our u, which we remember was t to the fourth plus 2t, and we have an answer. We could expand it out, put in limits or something and calculate it, but we don't need to right now. Just the idea is just to show you the technique. There's a plus c there. In physics, often we can deduce what the constant would be from the circumstances of the problem, so we don't end up writing plus c very often, but this is more of a pure calculus problem without the context. Okay, so here is an example from 2019. This is a pretty typical problem. It's one of those velocity-related drag force problems. So on part B, I skipped part A, but you'll see there's an expression for V, and we're asked to find the magnitude of the vertical displacement. So we know that we need to integrate because the vertical displacement would be the integral of the velocity function with respect to time. So we just rewrite delta y is going to be equal to the integral of this function. We would have bounds, and we'd use these numbers because they do want an actual answer, but I'm not going to take you there all the way to the end. We're just going to show how you can use U-substitution in this context to get your answer right. This e expression is e to the negative bt, so that needs a U-substitution. So we'll have u be negative bt, and then du equals negative b dt. We took the derivative of u, and we got negative b dt. And so dt in our function up here would be negative 1 over b du. This is important because we need this fraction to get a correct answer. Now we have the integral of e to the negative bt dt is going to equal negative 1 over b e to the u du. And so that just becomes negative 1 over b e to the u, because the integral of e to the u is just e to the u. And we put in what we took as u, and we have an answer. So again, we'd go back and we'd put in these numbers for a and b, and here, and notice there's a times 1. I took that, I ignored that, and we took it apart and we worked on the hard part, but that just becomes at. We have numbers, and we could have, if there's a time interval given, we could calculate a specific displacement. This does say as a function of time t, so we would find it for t. Okay. If you are not particularly good at this topic right now, don't worry too much. You really don't need a whole lot of proficiency because the examples are not that complicated in Physics C. And it's not going to be also very many points on the AP exam, just a few points here and there. So students don't really have to have a great proficiency with this technique to get a good score, 3, 4, or 5. Calculus teachers typically teach far more than is necessary for AP Physics C in this regard, and your kids will get lots of practice. By the time, particularly if they get to Calculus BC, they'll be quite good at U-substitution and can see it right away often and do it better than you can. You can postpone teaching this technique or showing students these problems until the end of the course, which is fine to do, particularly if you're not feeling very confident in this topic, or if your calculus students are almost all in Calculus AB. Then you can come back to it near the end of the year when the calculus teacher has done a good job of teaching it to them, and it'll be much easier for them. This is what lots of us do. And another technique would be, if you have a mix of students like I often do, is to give the Calculus AB students who haven't learned U-substitution something else to do, pull aside the Calculus BC students and say, here, I'm going to show you something. We're going to come back to it later in the year, or it'll be on the test for you guys, but not for that group of Calculus AB students, and show them the problems. Usually they're ready to go on those. If you want some additional resources, this is a nice video from Black Pen Red Pen that explains what's going on with the chain rule and U-substitution, which I didn't really teach you. It's not that long, and it's worth watching. And then the organic chemistry tutor is pretty straightforward. It's not just organic chemistry. They have a ton of videos on physics and calculus. They're, as I said, pretty straightforward. Bare bones, there's not much distraction, and there's good information there. Seems pretty solid. Students often like it. This is a YouTuber that I just discovered the other day. Nancy Pye has some calculus videos, maybe some other stuff, I don't know, but they seem pretty good as well. Here's a couple of resources that could be really useful to you and to your students. The integral calculator, and there's also a derivative calculator. Notice I put in a problem there, and it shows me the steps, how to do the problem. So you can bet your students know about this, or will find it shortly if on their own, if somebody doesn't tell them about it right away, and it's part in our derivative calculator. So that's just life nowadays, right? But it can be very useful for you as well if you get stuck. It'll often show you, once you learn how to enter it properly, it'll often show you exactly what you need to do. And then another website I like for calculus is Paul's Online Notes. That's from Lamar University. It has pretty clear exposition of what's going on with a lot of calculus techniques and ideas, as well as practice problems with work solutions that you just click to expand the solution, so you can read the problem, work it yourself, boom, there's the solution. So if you need to learn additional calculus, it's a great website. It's very deep. It has many web pages with lots of different stuff, more than you actually need for teaching AP Physics C, but it's good to know that it's there. That's all I have for today. Remember, what one fool can learn, another can. Here's another XKCD cartoon. I'm sorry, it's making me laugh. This little ass. Now the original expression becomes integral of u dv equals question mark, which looks easier, but I gotta run. Thanks for watching. Remember what one fool can learn, another can.